Hi everyone, welcome to another meeting of ChemSoc. I'm Nads, and I have here with me Ricardo and Tiffany.
Hi.
Alright, so today guys we will be doing some food tests. We will be testing for macronutrients, that's carbohydrates, proteins, and lipids. So we'll be using a number of food items like sugar, glucose, milk, cheese, etc. to test for the different macronutrients. So we are currently prepping. So let me just show you guys where we're at the moment. So we're prepping the food samples, adding them to test tubes so that we can carry out the test. So far this is our test tube rack set up with our test tubes, and Tiffany is currently prepping the samples that we need. So far we have oil, we have cheese, and we have syrup. This is some syrup. This is some fruit punch juice. This one is oil as well. Oh, this is sugar. So we have left to prep the milk, glucose, and egg. Yeah, so we have the egg left. All right. So the first test that we want to do is we want to do the reducing and non-reducing sugar test. Before we start anything though, before we start doing the test while we're prepping, we're just going to go through some of the theory regarding reducing and non-reducing sugars. So this is where we're at. So we're going to go through some of the theory regarding the reducing and non-reducing sugars at this time, and then we get back into the experiment. So we're doing food tests, and we know that food provides energy and nutrients, and the different components of our diet have different sources and functions. So we know that lipids, proteins, carbohydrates, they all have different functions. And we eat many complex foods which contain a mixture of macro and micronutrients. So our food tests are what we use to find out what nutrients or what different types of nutrients or different food contain. So there are different tests that can be conducted to see which nutrient is in our food. So starting with the reducing sugar test. The reducing sugar test is a chemical test that we use to verify the presence of a reducing sugar. And by reducing sugar, we are talking about sugars or monosaccharide carbohydrates that have a free aldehyde or ketone group. So we should know what an aldehyde or ketone group looks like by this time. And this aldehyde or ketone group is going to act as a reducing agent. What we find is that all monosaccharides are reducing agents, and then we have a few disaccharides such as lactose and maltose that are also reducing agents. So some of the examples we have here are glucose, fructose, the lactose. Those are monosaccharides, and then we have lactose and maltose, which are disaccharides. So Benedict's reagent is what we actually use to carry out the test for our reducing sugars. The reducing sugar test utilizes this solution that we're going to use today. It's a bright blue solution. If you know what copper sulfate looks like, then that's pretty much how it looks. But you're going to see it's a deep blue alkaline mixture of sodium citrate, sodium carbonate, and the pentahydrate of copper sulfate. The purpose of your sodium carbonate is to provide an alkaline condition for the redox reactions that are going to happen. Because remember that your aldehyde or ketone group is going to act as a reducing agent, which means something is getting oxidized, something is getting reduced. Your sodium citrate is a complexing agent, so it basically avoids the copper ions from degrading when you store the solution. When you expose the aldehyde functional group of the reducing sugar to the Benedict reagent, you will see the formation of a brick red precipitate indicating that you have a positive Benedict test. So in actuality, it is the aldehyde group of the sugar that is reacting with the Benedict reagent. Even though you have ketoses or ketones like fructose that can react with Benedict's reagent, the thing is that in its ketone form, it is able to undergo a process known as tautomerization. So that means it can rearrange its structure to form an aldose form of the sugar. And then that aldehyde group is going to react with the reagent. So our sodium carbonate, as we said, it provides a alkaline environment for the redox reaction to happen, and it converts the sugar into a strong reducing agent called enediol. During the reaction, the cupric particles, that's the copper 2 plus ions, are reduced by the enediol, and it appears as copper oxide, which is insoluble in water. So copper oxide, the copper ion which is in copper oxide is actually copper 1. So it's been reduced from copper 2 in copper sulfate to copper 1 in copper oxide. And that brick red precipitate that you're going to see would be your cuprous oxide, Cu2O. So when your concentration of sugar is high, you find that you get a more intense color versus when it is low. So the higher concentration of sugar you have, the higher the intensity and the volume of precipitate that you see. All right, so the principle of this Buret test, recalling that our Benedict's solution consists of copper sulfate, pentahydrate, sodium carbonate, as well as sodium citrate. That's what makes up the solution. What happens in the test or the reaction that takes place is where we see the cupric ions, that is the copper 2 plus ions, they react to the aldehyde group. The cupric ions are reduced to copper 1, which is in the cuprous oxide, and your aldehyde is oxidized to a carboxylic acid. So we can see the redox reaction that is taking place in the test. So how we're going to carry out the test itself, we're going to add 2 mils of our Benedict solution to approximately 1 mil of our analyte in a test tube. We're going to heat it in a water bath for 3 to 5 minutes, and then we're going to observe for a color change as well as the precipitate forming in the test tube. So this is a picture of the interpretation of the Benedict test. So you can see where the higher the percentage of sugar that is present, the more intense the red color that you're seeing. So it's moving from a blue color, which is the color of your Benedict solution or Benedict's reagent, and gradually goes up to a brick red color, which shows that you have a very high concentration of sugar. So you're seeing where it says 0.5 to 1 gram percentage, that's the aqua to green color there. That would be traceable amount of sugar. 1 to 1.5 1.5 gram percentage is that green solution or lime green solution. That's low. 1.5 to 2, that's the yellow solution. It's moderate, and from your orange, red orange, and your brick red solutions, that means you have a high concentration of sugar. So onto the non-reducing sugar test. The non-reducing sugar test is similar to the reducing sugar test, or non-reducing sugars are those that do not have a free ketone or aldehyde group. And compared to our reducing sugar, we know that those have a free aldehyde or ketone group. So what we find is that the non-reducing sugars, they can't act as reducing agents. Seeing that the reducing groups of the monosaccharides that make up these sugars are involved in the formation of glycosidic bonds to maintain the structure of the disaccharide or the polysaccharide. So compared to a monosaccharide where we know it's just one unit of sugar, so its aldehyde group is not bonded to anything, it is free, so it can easily act as a reducing agent. But for a disaccharide or polysaccharide, well, most disaccharides and polysaccharides, the reducing groups are involved in bonds or in glycosidic bond formation. So they are not free in solution to where they can act as reducing agents. And if you look at the structures shown, you can see that once the glycosidic bonds are formed, you're not seeing where there's a free aldehyde group present to react or to act as a reducing agent. So reducing sugars, for example, as we noted, sucrose and starch, they cannot reduce the copper sulfate like the reducing sugars would when they are tested with the Benedict reagent. So the acid is added, that's hydrochloric acid is added to hydrolyze any of the glycosidic bonds that are present in the carbohydrate molecules, and the monosaccharides that are formed as a result will have the free aldehyde or ketone group to donate electrons to the copper sulfate and reducing it and allowing the precipitate to form. So for our non-reducing sugar test, we're going to first add 3 ml of dilute HCl to our sample, add it to our water bath, which will be brought to a boil. Then we're going to neutralize the solution with some sodium bicarbonate until it is slightly alkaline. And then we are going to add 2 to 3 ml of Benedict reagent to the sample and heat for 3 to 5 minutes. So the first part of the procedure essentially is hydrolyzing the glycosidic bonds that we have. And once we neutralize the acid out of the solution, then we will be basically conducting a reducing sugar test after that, because the disaccharides or polysaccharides present would be broken down to monosaccharides. All right, so before we move on to the Buret test, which is for proteins, we are going to carry out the reducing and non-reducing sugar test. And while we add them to the heat bath, then we can carry out the Buret test. So let me just turn back on my camera so you guys can see. You made the glucose one? All right. So here we are. We have our sugar solution here. This is the sugar. Well, sucrose. This one. And we're going to make a glucose solution. Glucose. Oh. So this is the sucrose right here, and then we're going to make a glucose solution. So for our Benedict test, again, we're going to add about 2 to 3 mils of our Benedict reagent to the sample. We're going to stir it, and then we're going to add it to the heat bath or hot water bath. So this is our water bath that we're making. So we're just heating the water so that it can get hot. And then we add the test tubes to it. So this is our glucose solution that we're gonna be using. And this is our sucrose. So we're going to do both of them directly with the Benedict reagent. And then for the sucrose, then we try it with the acid. Because we did say that glucose is a monosaccharide and sucrose a disaccharide, but it is not a reducing sugar. But we're going to do the complete test for you guys. All right, so we're getting a dropper. This is our Benedict solution or our Benedict reagent. So I made it not long before the club meeting, and maybe at the end of the meeting I can show you guys how it's made. But I won't be making a new batch because we have a lot. So that is our Benedict reagent. And we're gonna take 3 mils, which this dropper should be approximately 1 mil. So we're going to add 3 mils to each of the test tubes. This one and the glucose. Yeah, I think so. Let me label them. Hi. So it's good practice in chemistry, of course, to label. So we're gonna label the test tubes. So this one is sucrose. And the next one is glucose. Alright, so we've labeled both of them. So now we're going to add them to our water bath, which is basically water in a beaker. Yeah. So we're gonna leave it for about 5 minutes. Should be 3 to 5 minutes. So we're gonna leave it for about 5 minutes. And we're going to move on to our protein test. Even though I think we had to Yeah, we have some syrup. Let me label it. This is the syrup. This is the fruit juice. Yes.
Okay. So now is nice that on people and certain real.
No, I don't want to get you. All right. All right. So we labeled the juice as well as syrup. So um we're going to do a Benedict test on these as well. Oh, so this is the syrup and the juice. So we're going to do it simply by just adding the Benedict reagent to it first, and then we observe changes. Afterwards, we will know whether or not we have a reducing sugar. And if we don't get a positive result for a reducing sugar, then we will do a non-reducing sugar test by adding HCl first. So I'm going to add 3 ml to each of these and also add them to the water bath. So we're going to add them to the water bath. This one looks very bright in color just because the syrup was red and I added the blue. So yeah, now add those. Yeah. All right, so we're adding those to the water bath as well. So now we're going to move to our Buret test, which we are doing with our cheese and milk. All right, so this is our cheese, and we're going to prepare a sample of milk for you guys. So while we're doing that, we're just going to go through the theory of the Buret test so you guys know exactly what's happening in the reaction and what we're doing for that test. Don't tell me. All right, so the Buret test is used to detect the presence of peptides, which we know are what make up proteins, are the basis of formation of proteins. So the test may also be used to quantify proteins present in a sample, but usually you don't use a Buret test for quantification. It is used mostly for qualitative purposes. So the test gives a positive result to any compound that contains carbonyl groups attached to a nitrogen or carbon atom. So you may find that it is not 100% foolproof to proteins because you may have compounds where they have a what you call an amide group, which is what is not protein, but they're not necessarily proteins. So that's actually going to give you a false result. So it's not 100% foolproof, but it's good for a quick, easy, qualitative test. So the Buret reagent, it consists of copper sulfate, sodium hydroxide, and sometimes sodium potassium tartrate is added to the solution. The sodium potassium tartrate is a chelating substance. So what it does is something similar to what your trisodium citrate does in your Benedict reagent. So your sodium potassium tartrate, it just stabilizes the copper ions. So despite the name of the reagent, it actually does not contain burette, which is a compound that is formed from heating urea. In this test, what you find is that the copper ion forms a pale or mauve coordination complex with 4 nitrogen ions from the peptide bonds when the solution is sufficiently alkaline. So of course you added sodium hydroxide to make the solution alkaline, and your copper sulfate is the main thing that is reacting in the solution. So you're just adding a chelating substance to basically stabilize the copper ions, and then you are adding sodium hydroxide to make sure that the environment is alkaline. So you can see in the diagram where the copper 2+ ion from the copper sulfate is forming a coordination complex with the 4 nitrogen atoms. So for a procedure, it's simple. All you're doing is adding 1 or 2 mils of your test solution to 1 to 2 mils of Buret reagent. So you're adding it in a 1-to-1 ratio. You add it, you shake the solution well, you allow it to stand for 5 minutes, and you observe the color change. Really simple and straightforward. So we're going to go ahead and do the Buret test. So let me show you guys what's going on again. So we have our milk sample. This is our milk sample. And we have our cheese sample here. So we just added a bit of water to it to prepare the sample. And then this is our Buret reagent. So just to note, initially it was this color. And remember, we said that the sodium potassium tartrate is used to chelate the copper ions, so basically to stabilize them. However, we do not and did not use any sodium potassium tartrate, hence why we're here. We're going to go ahead and use, this is the copper sulfate along with sodium hydroxide. So we're just going to go ahead and use this for the test. All right, so guys, we also have egg white with us, or albumin. So we're also going to do a test with that. So we are adding about 1 to 2 mils. I'm going to give it a little stir. We're going to add 1 mil to the egg white just because it's not a lot. We're going to shake it. And as you can see, it's looking a bit purple. Let me see if you guys can see what. So you should be seeing the purple color. There we go. So you should be seeing the purple color. Camera focus. There we go. So as time goes on and you allow it to sit some more, it gets darker and darker. So you see a dark purple color. I assume that everybody is seeing that. Yeah, so we're going to allow that to sit and we're going to do our milk. We're going to add about 1 ml to the milk as well. This is the milk. Right, as you can see, the color is changing. This is more like a mauve color. Yeah, because the milk was initially white. So it's not gonna be as purple as the egg white. So then we're going to do the cheese. The next here. So we're going to add it to the cheese. So as you can see, almost instantly, you're seeing the color changing. So it's turning more and more of a purple color. So because the cheese is thick, we're just stirring to get everything in there. But similar to the milk, it's a mauve color because cheese is orange or light yellow before we added the water and everything. And then now we have a mauve color. Yep. All right, so those are the 3 of them. So we have the milk, and this is the egg white. The egg white is pretty bright, but of course it was transparent before, so. And then this is the milk, and then we have the cheese. So pretty simple. So this is the progress of our Benedict test. Let me see what is 1, 2, 3. Which one is this? Oh my God. Guys, guess what? The writing on the test tube boiled off. I'm going to show you guys, or we can label it again and do it one more time. It didn't take long. So let me just show you guys. This one, there's a precipitate in the bottom of it. You should be seeing the brick red precipitate. Can you focus, man? There we go. So the solution is bright orange. So remember we talked about the results of percentage sugar, low, moderate, high. And then you can see the precipitate at the bottom of the test tube. Yeah. So let me look at another one. So of course I'm not sure which one this is because the labeling came off, but we're going to label them at the top or use tape or something to get it done and do it over again. So this one is still blue. Not sure which one this is. Well, it's kind of green, to be honest. Blue green. But there's no precipitate in it. So It's probably yeah, probably a traceable amount of sugar in it, because it's blue-green in color. It's not blue, because if I compare it to the Benedict's is really bright blue, and this is kind of green. Yeah. Next one. Let's see. This one is deep brown. Let me see. It's not quite red orange. It doesn't really look red. It's kind of like when you're going from yellow to orange, I guess, but you're not quite orange. So it's not as bright as this one, which this one is closer to red. And I'm not seeing a precipitate either. Yeah, I don't see a precipitate in the bottom. So let's do the next one. This one is nice and red. There is a precipitate. Let me turn it around so you guys can see. There's a precipitate there. It's a bit difficult to see because of the color of the solution. That is almost the same color the precipitate, but if you look closely, you should see the precipitate in the bottom of the test tube. All right. Let me try and see if this can focus. There you go. So you're seeing the precipitate there in the bottom. All right, so this would be a high sugar content, this one here. So I guess we're going to run those again while we're doing the other test, that is the iodine starch test, which for some reason I forgot to prepare the reagent for it. But while we are doing the theory for the test, I will go ahead and just try prep it in the meantime. So we're going to run the reducing / non-reducing sugar test again, so we can know which was which. We use new testing to compare them. And then let's go through the theory for the iodine starch test while we're doing that. All right, so iodine starch test is used to identify the presence of starch, as the name indicates. But what we find is that starch is a combination of two main compounds, that is amylose and amylopectin. So naturally, starch is a combination of the two. The amylose concentration is about amylose concentration is 10 to 20%, and the amylopectin is 80 to 90%. So most of starch is actually amylopectin. The amylose forms a colloidal suspension with hot water, so it's not completely soluble in water, but amylopectin is completely insoluble. So whereas amylose will dissolve to an extent, the amylopectin will just stay out of solution. The iodine test, as I said, is what we use to detect the presence of starch. So this is a qualitative test, not quantitative. So you're not you're not necessarily determining how much starch is there. It is possible to do titrations to determine that, but you're trying to detect or tell if starch is present. So to make up our iodine solution, we're going to be using 5% iodine and 10% potassium iodide. And why we're using potassium iodide is because iodine itself is not soluble in water. So if you put it in water, it won't dissolve. So the iodine reagent that we're using, known as Lugol's iodine and Lugol's reagent, it is made by dissolving 5% of your elemental iodine in 10% of potassium iodide. So your molecular iodine, which is I2, reacts with the I- ion that is in your potassium iodine, and it will create an anion, which is I3-. So this anion is polar, so it can dissolve in water. And this linear tri-ion complex, it is able to slip into the coils of the starch structure. So when it combines with the coils of the starch structure, or it slips into the structure of the amylose and amylopectin, then it produces this intense blue-black color. So for our procedure, we will be adding 2 to 3 drops of Lugol's reagent to the food sample. If we're using a liquid sample, we're just going to add 2 to 3 drops to 1 ml of sample. So a blue-black color is going to tell if starch is present or not. So I'm going to show you guys how I make the Lugol's reagent. I'm going to show you guys how I make the Lugol's reagent. So here we have with us some iodine. Show you guys what it looks like. Yeah. That's the iodine. Oopsie. And our potassium iodide is white in color. Let me just show you guys what it looks like. This is potassium iodide. So we're making 5% iodine, which 5% weight per volume is 5 grams of iodine in 100 ml of water. I don't want to use 5 grams. I'll use 2.5 grams. So that means I would add 50 ml of water. So I'm going to add conical flask. Better to use a beaker, but the beakers are occupied right now. I'm going to add a conical flask to our balance. And this is an analytical balance. I hope you guys can see the numbers. It's very dark, but I hope you can see. There we go. We're going to zero the balance. And then we're going to weigh out 2.5 grams of iodine. So the scale itself is a bit difficult to see, so you guys may not be able to see the numbers while I'm weighing. Yeah. All right, so while I'm weighing out this to make the Lugol's reagent, Tiffany is currently reconducting the Benedict test. So we actually have 2.6 grams. Oh Lord, that should be clear. There we go. We have 2.6 grams of iodine. Close enough. And then we're going to do potassium iodide. So it's a 10% potassium iodide, which means 10 grams in 100 ml of water, which I'm just going to use 5 grams. I'm going to add it to the same conical flask. So I'll just add it back to the analytical balance and zero the balance. There we go. So once we zero the balance, then we're going to add in 5 grams. Since we said we're going to use 50 ml of liquid, we would just half the number, well, the amount of potassium iodide we add. So I'm just going to add it. You guys may not be seeing just because I'm using both my hands. So I'm just going to add 5 grams, add it until you see 5 grams on the analytical balance, which an analytical balance is a lot more accurate than what you call a top pan balance. Top pan balance usually has two or three decimal places, so it's not as accurate and it has a lower precision. And also analytical balances are covered or surrounded. So when you close this, it actually reduces the air resistance. So we have 5.247 grams, which is good enough. So this is what we currently have. So that color, of course, is the iodine. And then we're going to dissolve this in water, 50 ml of water at least. So you eventually have to transfer it to a larger container. And this is the reason why you wear gloves in the lab. My gloves are in the bag, but I forgot to put them on. So we're just going to add distilled water to this conical flask and dissolve all of this. We're going to move it to a bigger conical flask or beaker so that we can hold 50. Well, this should be able to hold it. Yeah, because this is a 100 ml conical flask. So let me get some distilled water to add to it. This is our distilled water. We're going to add it. We're going to add approximately 50 ml. So we have a 40 ml mark and a 60 ml mark. Because we're using this side, the side that goes up to, let's see. So this is the side that goes up to 100. You're not using this side, you're using this side. So you have a 40 mark and a 60 mark. So we're just going to get it in between that mark to get 50 mils. That looks like it's between. So we're going to mix this. So this pretty much looks like iodine, right? So this is the Lugos reagent. We're going to add it to our food samples to determine if we have starch present. Right. So this is where we have set up our rerun of the reducing / non-reducing sugar test. So this time I added the labelings at the top so they won't come off. So for our samples for the starch test, we're going to use bread and so we're going to use some bread and some cereal and rice. This is the cereal. This is the rice. Okay. And this is the we're just going to use our test tube to add about 1 ml of our Lugos reagent here to our samples. I think I had cornflakes as well. So let's add that to the dinner table. Right there, so right there. Lunch is served. So we're just going to add about a ml or a couple of drops actually of our reagent right here to our samples. So let's do the cereal. So if you can see, it's really dark in color. It's a blue-black color, but it's very hard to see the blue part of it. So iodine, let's see if I can. So when you add it to the cereal, that's why it looks like blue-black. Almost black, to be honest. And we're gonna add it to the rice. So we know that the iodine has a brownish yellow kind of color, right? As you can see in the test tube. Not the test tube, in the dropper. When we add it to something that has in starch, no longer has that color. It has this dark blue-black color, as we said. Right? So we're going to add it to the bun. So we're seeing the blue-black color on the bun. My good bun. Then we're going to do the cornflakes, which cornflakes has in corn, so you expect it to have some starch. You can see the same blue-black, and we're going to add it to the bread. And of course, we're seeing the blue-black color on the bread. So that's pretty much the starch test. That is very straightforward. If you're looking at the outer edges of the bread, let me see if I can hold it up for you guys. If you're looking at the outer edge of where the reagent is, it looks slightly purple. Don't know if you guys can see that. But in reality, of course, we describe it as blue-black. Why has my camera gone blurry? I hope that you guys are seeing. So as I said, around the edges, which is around the edge of the reagent, it looks a bit purple, but it's blue-black. So the starch test is pretty straightforward and simple. So we use some cereal, some rice. This is cornflakes, bun, and bread. I think the bread is the clearest one. All right, so the test that we have left is the lipid emulsion test using ethanol. So we have some ethanol here. We're supposed to use 95%. I think this is 100%. So I'm gonna have to dilute it. Or we could try using the 100%. Why not? So this is the oil that we have to do our lipid emulsion. All right, so let's go to the theory for lipid emulsion real quick, and then we can get to do the test. Meanwhile, this is ongoing. So as you can see, some of them have already changed color. This one is orange. That looks brownish. This one looks kind of blue, green looking. All right, so we are going to go through lipid emulsion. All right, so the test is done to show the presence of lipids in a substance. The long hydrocarbon chains of fats and lipids cause them to be non-polar in polar solutions. So if you add some oil or some butter, etc., that is a fat or oil or lipid, which is the correct term, you're going to find that it does not mix into the water, which water we know is a polar substance. So to carry out our lipid emulsion test, we're first going to dissolve the substance, or attempt to dissolve rather, in ethanol, and then we're going to add water to it. If lipids are present in the mixture, then it will precipitate and form an emulsion. So basically, it will precipitate out of the ethanol and form an emulsion because you're adding the polar water to it. So we're seeing the structures of some common lipids. So we have triglycerides. We also have free fatty acids, as well as a phospholipid and cholesterol. All right, so the procedure is real simple. All we're doing is to add 2 milliliters of 95% ethanol to our food sample, and we're going to shake well, allow it to set in the rack for 2 minutes, and then we're going to add 2 cm cubes or 2 ml of distilled water to it. If we observe a milky white emulsion, that's a positive result. That means lipid is present. If the mixture remains clear, then that means we don't have any fat present in the sample. So we're going to use oil. Let's see. And we're going to add 2 mils of ethanol to it. All right. So let's go back to the experiment. So we're going to use oil. So this is our oil. We're going to add ethanol to it, about 3 mils. So the dropper is approximately 1 mil. So we're going to add 3 droppers. That's 1, 2, 3. Alright, so this is what it looks like. I'm going to try to mix it around. So as you can see, kind of separate. And to try to mix it so that the oil can go into the ethanol. Maybe I should use the stirring rod to do that. Alright, so this, I'm going to try to use the stirring rod to mix the oil and the ethanol as much as possible. So this is how it looks. And as soon as I stop mixing, it starts to burn it back. But that's expected, of course, because ethanol is also polar. Yeah. Alright, so we're going to allow it to sit and then we add some water to it. So in the meantime, we have our reducing / non-reducing sugar test. So we're similar to what we saw before. So these are the ones we had before. And from, so as you can see, it's a similar thing that we have here. So this is the sugar or the sucrose that we have. And it's the blue-green solution. So we did say blue-green means a low concentration of sugar, but we also know that sucrose is a disaccharide, and it is not one of the disaccharides that is a reducing sugar. This is the syrup. So this one is the orange one with so much precipitate at the bottom. And we all know that syrup has in glucose, and I'm pretty sure it has in a lot of fructose. So yeah. So this is the fructose. So it's matching what we had before here. This one is the glucose. So this is the brownish looking one that we had, and it has some precipitate at the bottom, some brick red precipitate. Let me hold this up for you guys to see. I'm trying to get the light. There we go. So you can see the brick red precipitate at the bottom of the test tube. So that one is glucose. So this is what we had before for the glucose, since we're matching them. And this is the juice. which this looks brownish, so I can assume it has some sugar in it, but it probably has a lot of other stuff in it as well. Why it looks this color. So that's the one that we had before. So this is the juice. I mean, it's clear that it has some sugar in it because it has kind of a tint as if it's going to orange, but not quite there. It's more just brown. But of course, we know that juice has a lot more things in it than just sugar. So this says this whole thing separates. Which that alone can tell you that you have liquids, but we're going to add the water to it and mix it. For the sugar, we're going to do that one again, but we're going to add acid on it first. So we're going to add some HCl, and then we add the Benedict to it, and then we boil it. So first, let's do the fat emulsion test. I'm just going to add some water to it. And as you can see, you're going to see this milky white suspension. So it wasn't this milky white before. See that? Let me hold it here for you guys to see. There we go. So this is the milky white suspension that we're talking about. Even though we had a cloudy suspension before, when we added the ethanol, that's mainly because ethanol is polar, not as polar as water, but it's polar to where not all of the oil is going to mix into it. And then when you add the water to that, this is what you call a colloidal suspension, emulsion. Colloidal suspension. This is an emulsion. So it pretty much looks like watery milk, if that makes sense. Like a true water from milk, basically. So that's the result for the emulsion test. So again, we're going to do the sugar, and you want the syrup again? The syrup and some fruit juice. So again, these are the tests from the Buret. We let them sit in. So the one on the far left is the cheese, as you can see on the labeling. The one in the middle is the milk, and the one on the right is the egg white. All of them are purple or mauve. This one is the sucrose, and we're going to do one with some syrup and one with some what am I saying? Some juice. So what we're going to do is add the acid so it can hydrolyze any disaccharides that are present, and we're going to see the difference in the results that we get when we add the acid to it. Acid that we're using is HCl. So we're going to add a bit of HCl, mix it, then we'll add the Benedict. Then we neutralize it with some sodium bicarbonate, and then we add the Benedict reagent. All right, guys, so just a recap of what we did today. We did our potassium iodide starch test using Lucas reagent. We utilized Buret reagent, which is a copper sulfate and sodium hydroxide, to make the Buret reagent, and carried out the Buret test for proteins. And then we did the reducing / non-reducing sugar test. Well, the non-reducing part is what we're going to do now. and we had done the fat emulsion test. There is another test for fats that you can do. I'm just going to do it on this paper that I have using some butter. So this is the butter I'm going to use. It's just a smear test. This is something you can do at home. So you basically smear it onto the paper. And eventually you're going to get what you call a translucent spot on the paper. So as you can see, the paper is not completely transparent anymore. When you leave it over time, it gets more and more translucent. So that's the easier test for fats or lipids. The smear test, you just use a paper, something you can do simply at home. Smear the substance on the paper, and the translucent spot will tell you that you have a fat. The difference with that and something that is not a fat is that the paper is going to get wet, but eventually it will dry and it will look like this again. But with this, it's never going to go back to this. So we're at syrup and fruit juice. So we have the sucrose, the syrup. We're going to add some acid to it. Just wash out the drop. Alright, so I'm going to wash out the drop that I had. We're going to add some acid first to them. And then we're going to neutralize that acid. So the acid is going to break the glycosidic bonds, any that are present. Then we're going to neutralize that acid so that we have slightly alkaline solution. And then we're going to add the Benedict. Because the Benedict has to be in alkaline solution. So we're going to do the sucrose first. We're gonna add about 2 mils of acid. Or 1.5. I think maximum to do that. Once we follow ethanol blue litmus paper. Ethanol blue litmus paper. Alright. So here we have the acid added to our 3 test tubes. So we're going to just stir it so that the acid can combine throughout the whole mixture that we have. That's the syrup, and this is the sucrose. So we shake it, make sure the acid is all throughout. And then we're going to add sodium bicarbonate. You can also use sodium carbonate. Both of them are carbonates, just one is stronger than the other. The carbonate is stronger, but we don't have any sodium carbonate, so we're using this as substitute. All right, so we're going to add the sodium carbonate to it. We're just going to do a pH test using some. This is universal pH paper. You could use red or blue litmus, but red litmus is for acidic solution. You test the acidity. Blue litmus is for alkaline. The universal one works for anything really. So we're just gonna take off a piece of it and test the pH of each of the solutions. Then add some sodium carbonate, bicarbonate, and see when it gets neutralized. So this is so this is acidic. So that's the pH paper, and that's the scale that we're using. So it's acidic. So our aim is to neutralize the acid, and then after neutralizing the acid, then we're going to add the Benedict. That's also acidic. All right, so all three of them are acidic. So based on this, figuring that this one here, the pH is about 1. I mean, we just added HCl to it, and the HCl was about equal quantity to the sample we had. So it's highly acidic. So we're going to have to add a good amount of sodium carbonate to neutralize the acid, and then we're going to test the pH again. Once it's neutralized, actually when it's slightly alkaline, then we're going to add it to the water bath with the blend. So we're going to add the sodium carbonate. As you can see, there's a lot of fizzing. A lot of fizzing. So we'll probably add smaller amounts each time. And that's obviously because the acid is reacting with it. Hopefully this will go over. Alright, this one not so bad. Alright, it will go over. Again, bet with the measure the pH now is still active. And I'm behave the mostly. So this one is the fruit juice. Not bad at shake it. Jesus. Jesus. Alright, this stuff. Alright, we'll test them again. This one's still a bubble. I don't know what in there. Probably the other stuff are in the fruit juice. Likely. So we're going to test the pH of this is the sucrose solution. It is still acidic. It is still acidic. And it look like one, you know. It still look like one, honestly. It even move. So we probably have to add a couple spatulas as well. of carbonate to it. This one's still a form. So we kind of stop now. Alright, so we're going to add a couple of spatulas. Oh, Jesus! And I bet it's still acidic and behaving the most way. I guess you can add it till it stops. Please. Yeah, we're just gonna add it until it stops fizzing. And when it stops fizz, then I guess it should be neutralized. And then we'll add a little more to make it slightly alkaline. You know what we should do? A day in the life of a chemist. Because can't imagine how often these things happen. Guys, an update. This was our Buret solution. This thing fully form a precipitate in other something. Look at that. Like it's separating, but remember that we didn't put any stabilizing agent. That's why it's doing that. So when you don't use stabilizing agents, you kind of just have to use it quickly. So this one can store. The Benedict can store because we had put the trisodium citrate. Jeez. This one stop. This is the sugar. It's not fizzing, but I have a feeling it still has to be. But we shall see. See the volume go down? The volume go down? I mean, I lose my scroll. Oh. That one is a syrup. Still fizzing. Like it no one done fizz today. I'm going to add some to the fruit juice. I feel like that over. There you go. Huh? What?
Benedict Solution. You put the Malta in?
Yeah. It's in here.
No, the Malta.
Oh, the Malta? No.
You can put the milk and sesame paste.
So this is sugar. This is syrup. Yeah. So we're going to test the pH again and see how far it reaches. Um, so we're testing the syrup. If this thing ever still acidic, you see? It acidic. It does when it touch on the side. Oh, it's still a react. It look like it's in alkaline people. False alarm. Right.
But look how much it gets
It's acidic.
Definitely connected very acidic. Oh my god. So learning.
Here what? We're going to make over the solution and we're going to add 2 drops of acid. Yeah, that's what we're gonna do. Or 2 to 3 drops of acid. Because we don't have all day to be doing this. Because it literally not finish. You go to just put the liquid in there. I think it's probably because the acid was concentrated at HCl. So what we're doing now is to make the sodium carbonate into a solution. See, it is an alkaline solution. There. Yeah, so it's supposed to look. You see that? You see that? Yeah, so it's supposed to look like this. But I don't want one. So we're just going to make it into a solution. Add some more. And then just pour it into this. And pray that they don't fit anymore. Alright. So again, a recap before we go to question. You see much time I recap because if I can't answer the question, then so we did lipid emulsion test. We did Buret test, and a Buret consists of copper sulfate and sodium hydroxide. The chelating agent is sodium potassium tartrate, which we did not put, which is why our solution is separating like this. For our iodine starch test, we used our Lugos reagent, which is iodine 5% and 10% potassium iodide. For our reducing / non-reducing sugar test that we have done and is still ongoing, we use Benedict's reagent, which is our copper sulfate with sodium, trisodium citrate, and why I forget why I use metal something. Sodium carbonate, my God. Which for this experiment, I substituted the sodium carbonate with sodium bicarbonate. Which other test did we do? I think that's it. Yeah, I did emulsion and everything. All right, so we're going to go to questions, and then when we're done, we will. Great, we get one of them alkaline. Praise God. Look like 8. Nice. So we're going to go to questions in the meantime that we're doing this because the thing just keep on a phase. And then by the time we're done, we should have everything in order. The results, that is. So all that we're going to do is once we neutralize this, to test the pH to see that it's slightly alkaline, then we add our 2 or 3 mils of Benedict. We add it to the water bath for 5 minutes, and then we're good to go. Yeah? Yeah. So question time, people. We've been here for a minute, I would say. So question time before we go. So the first question is, the Buret test is used to detect the presence of lipids, proteins, reducing sugar or starch. I'm seeing one answer, 2 answers. Anybody else? All right, I'm seeing 5 answers. The correct answer is proteins. That is B. The first person to get that correct was Ciandre. So Ciandre gets that point. So our next question. The next question is, which of the following reagents contains copper sulfate? Is it A, Benedict and Lugol's? Is it Buret and Lugol's? Is it Lugol's and lipid emulsion? Or is it Buret and Benedict? Which pair of solution has or contains copper sulfate? Let's see. I'm seeing answers. Are they correct though? Are they? I'm seeing D, and the correct answer is indeed D, because the amount of times me recap, you should get the answer by now. So the Buret reagent has in copper sulfate along with sodium hydroxide, and your Benedict also has sodium hydroxide along with sodium trisodium citrate and sodium carbonate or bicarbonate. So the first correct answer I'm seeing is Ciandre, so Ciandre gets that point. Let's go to the next question. This is a 2-point question. Why is hydrochloric acid used in the Benedict test for non-reducing sugar? And that's what we're doing right now, so you should know why we're using hydrochloric acid. 2 points. Why is hydrochloric acid used in the Benedict test for non-reducing sugars? Any answers? Any takers? It's a really easy question, you know. Answers, guys? I'm seeing one answer. Are there any other answers? All right, so I'm seeing an answer from Stephanie that says it breaks the glycosidic bond, and that is the correct answer. So we utilize the hydrochloric acid in the Benedict test for non-reducing sugars, because the hydrochloric acid is going to break the glycosidic bond of the non-reducing sugar, making it a monosaccharide that can participate in a redox reaction. So next question, so Stephanie gets those 2 points. Those were easy 2 points, guys. We're on to the next question. So our question is, all of the following are reducing sugars except, let's see the answer. All of the following are reducing sugars except, let's see, I'm seeing some answers. The first correct person I see is Mikkel. The correct answer is sucrose. Almost all of these are disaccharides. So maltose, lactose, and sucrose are disaccharides. Galactose is a monosaccharide. However, all of them are reducing sugars except sucrose. So Mikkel gets that point. Next question. This one alkaline? Oh, okay then. All right, so this question is, what is the purpose of sodium hydroxide in the Buret test? Why did we add sodium hydroxide in the Buret test? Why did we add sodium hydroxide in the Buret test? What purpose did it serve? Any answers? Something that is happening. Oh, no. To create an alkaline environment to give an alkaline medium. So Stephanie was the first with that correct answer. So Stephanie gets 2 points. Another 2 points. We're on to the next question. This one? All right, so the next question after this. So Stephanie gets that one correct. So let's move to the next question. The next one should be a 1 point question. All right, so our next question is, what percentage of starch is amylopectin? Is it 50 to 60%, 10 to 20, 60 to 70, or 80 to 90? Let's see the answers. Is it 50 to 60, 10 to 20, 60 to 70, or 80 to 90? I'm seeing some answers. The correct answer is 80 to 90. The first person with the correct answer was Stephanie. So Stephanie gets that point. We can't make Stephanie a beat. What's going on? That can't work. Next question. What does a yellow result for a Benedict test mean? Alkaline? Oh. What does a yellow result for a Benedict test mean? I'm pretty sure we looked at it. We got a green one for ours, and that was, well, I'm not going to tell you what. We told you it was. Is it a low, high, moderate, or no reducing sugar? I'm seeing some different answers. I'm seeing C. I'm seeing A. Which is it though? Anyone else has a different answer that you think is correct compared to the other answers that were given? Or if you want to change your answer, that's fine as well. But just know the answer when you change is the final answer. Can't. Miguel, why are you asking me the answer? You can't ask me the answer. You have to tell me what your answer is. A yellow result for Benedict test. Does it mean low, high, moderate, no, or no reducing sugar? So now I'm seeing C, I'm seeing A, I'm seeing D, and Miguel is asking me this. You can't ask me. So the answer for a yellow test, it is C. I think Joffine got that. So Joffine is correct. Joffine, that is 1 point for you so far. I don't know what's happening in Joffine today. 1 point for Joffine so far. Miguel, no, it is not D. I don't know how you're going to ask me what the answer is. Not D. So yellow is going to give you moderate. Anything above yellow, whether it's orange or red or close to brown looking, that's a high concentration of sugar. So our next question, I think this is a 2-point question coming up, is it? Yes, it is. How would protein be quantified using the Buret reagent? So we did say that Buret reagent, you use it to detect the presence. You use it to detect the presence of, protein, but you can also use it to quantify. It's not the most accurate method to quantify protein, but give me a way in which you can use this this Buret reagent to quantify how much protein you have in a sample. Let's see who's thinking and who was paying attention to this slide when I was talking. Mikkel says titration. Stephanie is asking me the answer. That cannot work, Stephanie. Titration. Anybody else has any other answer other than titration? It basic now? Praise the Lord. Oh, it's sample gone. C. says intensity spectrophotometer. Anybody has a different answer? We know quantification methods, right? Your quantification means you're trying to find how much Qualitative means you're just trying to detect or confirm the presence of something. Quantitative, you're trying to quantify how much you have. So, Mr. Titration, I see intensity, spectrophotometer. Any other answers? Or if you want to change your answer, you can do so. Just know your final answer is what I will use. All right, so I'm going to take it that we don't have any more answers and nobody wants to change their answer. So C and Dre is correct. You would use the intensity or spectrophotometry to measure the quantity. Titration wouldn't work so well because you would have to have standard solutions, which especially with this Buret thing that separates readily, it might be hard to use it to do an accurate titration. So the next question, I think that's a 1 point question, 1 mark question. What color change is observed for a positive Buret test? Is it blue to green, purple to blue, blue to purple, purple to pink? Let's see the answers. What color change is observed? This is an easy one. This is easy 1 point. Easy peasy. I'm seeing some answers. Mikhail say A, B, C, D. I don't know if he's saying his alphabet. I don't know what that is. I'm seeing C from everybody else. The correct answer is indeed C. The first person to get that correct was Stephanie. So Stephanie gets another point. I don't understand how to make Stephanie come and beat me today. That's crazy. So that was a 1 point question. I think we have a 2 point question after this one. So let's move to the next question. So our next question, which you just skipped, all right, so this is our question. What is the positive result of a lipid emulsion test? When we finish the test, what result did we get that indicated that we had lipids present? Let's see the answer. Let's see. I'm seeing one answer. Anybody else? All right, so I'm seeing 3 answers. Jophine is working so hard to get the point. Stephanie said milky emulsion and Jophine said milky white emulsion. What do you think? Stephanie said milky emulsion and Jophine said milky white emulsion. Milky white? Okay, we're going with milk. The judges have decided and we're going with milky white. Maybe the milk could be cherry milk, so it could be pink. I don't know. So we're going with the milky white from Jophine. So Jophine gets that point. So that is a lesson learned, people. When we are describing in chemistry, we must be specific. Josephine gets that point. Well, it's 2 points. Oh my God, I'm so sorry. Yeah. Yes, Stephanie. We are serious. Milky white emulsion. So we are going to the next question. This asks which pair of tests are quantitative? Is it the lipid emulsion and Buret, iodine and Benedict, lipid emulsion and iodine, or Buret and Benedict? Which pair of tests are quantitative? Which pair of tests are quantitative? I am seeing B, I'm seeing D. Anybody else has an answer? I am seeing A, I am seeing C. Anybody else? Mikhail change him answer from B to D. Okay. Josephine said D. Anybody want to change their answer? Anybody else wants to change their answer? Mikhail said E. C. Okay, so locked in. So the answer is Buret and Benedict. I mean, we just talked about Buret being quantitative. And Benedict is quantitative because obviously we use the color intensity to see what range of sugar content the sample contains. So C. Andre has the correct answer. So that's plus 1 point for C. Andre. Let's go to the next question. All right, so you have 30 seconds to tell me another and more accurate method of quantification of protein. And the time started already because you already did the question. So you have 10 seconds left. But 10, not 10, 20. What is another more accurate method of protein quantification? 10 seconds. I guess we're going to a minute then. So what is another method that we can use to quantify? To quantify protein, but it is more accurate than a Buret test. So we said Buret test is mainly qualitative. Can be used quantitatively, but it is not the most accurate method for quantification. Couldn't finish search Google or find the answer. And this is worth 3 points. 1, 2, 4, 6. 1, 2, 3, 4, 5, 6. Okay, so I guess nobody gets those 3 points. Or you can tell me after we show you guys what's going on in the water bath. So we had neutralized the solutions, and Kiana says spectrophotometry. That is that is so wide and broad, Kiana. what exactly am I doing with spectrophotometry? Do I just take the sample and put it in the spec? What do I do? So similarly, I think Andre was the one who answered correctly to say you utilize the Buret test for quantification by using spectrophotometry. So what you would do is to add the Buret reagent to the sample, and then you measure the intensity of the solution in a spectrophotometry, in a spectrophotometer against a control.
These came back from a search.
Right? So how exactly would you utilize, or what other method can you use for protein quantification? There is one major universal method that is used all the time, especially if you do biochemistry. Use that thing till you're tired. So this is our sucrose. This is sucrose? No, this is syrup. And this is how it looks. You probably can't see anything. Well, probably because there's nothing there. But this is the syrup that we had. Remember that when we did it without the acid, which was this one. So I guess most of the syrup is like fructose or glucose. Simple sugar. So the acid really didn't do anything for it. This is the juice. I don't know if you guys are seeing it clearly. There we go. So this one is the juice. And as you can see at the bottom, there is some precipitate there that was formed. My camera keeps going out of focus for some reason. So the precipitate is there that was formed. So that means we had some complex sugars in it, whether it was sucrose or I don't know, some starch, I have no idea. And this one was our sucrose. So the solution is, it appears a bit clear, but there is precipitate at the bottom. So there you can see the precipitate. If this thing would just focus, my life would be such a breeze. There we go. So with this sugar, which one was the sugar again? This was the sugar that we initially had. It was green, blue-green. And this is what we have now that we added acid, and then we get a precipitate. So that means the acid hydrolyzes the glycosidic bonds in the sucrose to reform the alpha glucose and beta fructose that makes up sucrose. And that's the end of the experiment. Nobody not go to the answers yet? The 3 points just got to waste. Oh my gosh. All right, so I'm going to tell you the answer. The most common universal method of protein quantification is called Bradford Assay. So it's where you utilize this thing called Bradford Reagent. You react it with a standard protein called bovine serum albumin or BSA, and you use that to construct a calibration curve. And then for any other sample you have, all you have to do is react it with some Bradford reagent, measure the absorbance, and then you just extrapolate the value of the concentration of your calibration curve. So the answer was Bradford Assay. I guess those 3 points went to waste, but this is the end of today's meeting, which did feel really long. The points from the questions. We have Ciandre with 4 points, Stephanie with 6, Mikkel with 1, and Jocelyn with 3. And we know that for each point that we get, you get 10 points on the leaderboard. So Ciandre would have 40, Stephanie has 60, Mikkel has 10, and Jocelyn has 30. So Stephanie is leading right now. So guys, that's the end of today's experiment. We will be seeing you guys next week for another experiment. Not sure what we're doing next week as yet, but we will let you guys know. And that's the end of today. Bye.